thank you everyone for joining today, and particularly to our speaker, Dr. Luca Labate, who is a senior researcher at CNR Inno in Pisa in Italy. Today he's going to speak to us about an application of compact laser-driven electron accelerators toward novel approaches to radiotherapy. So when you're ready, Luca, please feel free.
I'm ready. I'm ready. Just a minute because I don't. Okay. So thanks to Hannah and to the organizers of this seminars. For those who don't know me, I'm from the National Institute of Optics of the CNR. CNR is the Italian National Research Council in Pisa. Our lab is based in this CNR campus, which is the biggest, actually, the biggest campus, CNR campus in Italy. And in particular, I'm with the Intense Laser Irradiation Laboratory Group, which is, as you can see from here, is currently made up by something like 15, more than 15 people, just mentioning the scientific stuff. And this is a map of our lab with the current and future equipment. So we basically, our main laser is a 250 terawatt system running at 5 Hz, 27 femtoseconds. No, even less now. Then we have a laser development activity for which we use a kilohertz laser system providing 20 millijoule energy pulses at at 2 microns. This is a sort of if I have time at the end of my talk, I will touch this point. We have a laser development activity on this. And then we are procuring 100 Hertz and 1 joule laser system for applications requiring a high average flux of particles. We will see. I think we will delve into this in the core of my talk. And we'll also have, we are having a sort of major rebuilding, reorganization of the lab, since we are now building an underground bunker for high average flux particle applications. The role of the ELIL, Intense Laser Irradiation Laboratory, in eupraxia or CNR Inno, we will serve as the eupraxia national node in Italy, and we will also act as a laser test facility for eupraxia. We'll see, of course, some of the activities related to eupraxia in my talk, but what we want to see is this activity which is strictly related to eupraxia, which is the study of advanced acceleration schemes for the production of high quality beams. And for instance, we are working on this resonant multipulse ionization scheme, REMPI, which is one of the possible schemes foreseen to be used for eupraxia facility. So the main research fields of the group, the ELIL group, of course, are in the laser-driven particle accelerators, namely electrons and the production of secondary radiation sources, and protons and light ions. And we both perform, I would say, fundamental studies. For instance, here I'm mentioning a paper on proton acceleration, as well as applications in different fields. We also have a non-negligible, I would say, activity in ICF, inertial confinement fusion. And we study, for instance, laser-driven instabilities and diagnostics for ICF. I would like just to mention this recent paper just as an example of the activity carried out over the past couple of years. This is a paper on the application of laser-driven proton beams, accelerated through this TNS-A scheme to the quantitative elemental analysis of specimen using the so-called PIXE. PIXE stands for proton-induced X-ray emission diagnostics. And here, for instance, we show that using a compact laser-driven proton accelerator, we could measure the elemental composition of a specimen with a resolution very close to well-established PIXE techniques based on conventional accelerators. So this is the contents, tentative contents of the talk. Depending. Then I will stop at some point if I I will see them running long. Since I was told that some of the people in the audience could not be of in this plasma acceleration field, I will just introduce you very quickly to the topic of laser plasma electron acceleration. And then the core of my talk is on the R&D activities we are carrying out focused on to radiotherapy with VHEE beams. VHEE stands for Very High Energy Electrons, laser-driven Very High Energy Electrons beams. So I will introduce you to the current scenario in radiotherapy and of course the motivations for this work. Then I will very quickly give you a survey of the experiments and on the other labs active in this field. And then I will very quickly show some recent results from our group. And I will frame all these activities from us and from others into this the ongoing efforts to study, understand, and possibly use this relatively recently observed flash effect. And if I have time at the end, I will show you some of the results of our R&D activity on the development of novel high repetition rate lasers. So very quickly, going through just an introduction to this laser WakeField acceleration. I mean, if you are here, of course, you know that ultra short and ultra intense lasers can be used for accelerate electrons in this case. The basic ingredients for this is the excitation of a plasma wave, which occurs in the wake of the laser pulse. And then, of course, you let some electrons to surf the wave and get injected. And if they are on the right phase, of course, getting accelerated. So the main driver of the plasma wave is the laser pulse, of course, through the ponderomotive force, which is a force dependent on the gradient of the intensity. Then, of course, you have many scenarios. I mean, this is a relatively old picture. Then, of course, in the last 20 or 30 years, there were many. There has been a very strong evolution even in the understanding of the physics of the laser wakefield acceleration. Of course, you have sort of quite mild resonance of this process. So looking at this picture here on the bottom right, you can see this shows the intensity of the field of the accelerating field, so the magnitude of the accelerating field as a function of this quantity here, which relates the duration of the pulse through this L RMS, and the plasma wavelength. This is the wave vector. So as you can see here, of course, since the plasma wavelength depend on the density, there is a sort of of interplay between the density of the plasma and the duration required for efficiently exciting the plasma wave. So I think you know it. The main and the most I would say appealing advantage of laser Wakefield accelerator is the possibility of accelerating particles over a very short path, mainly due to the fact that the maximum electric field, the amplitude of this field, is several orders of magnitude higher than the one which you can reach in conventional accelerators based on RF-based Linux. So we are talking of 3 to 4 orders of magnitude higher fields. And this, of course, makes this kind of accelerators very compact in size with all the nice consequences of this fact. So just to give you an idea for those who are not in the field, this is in our case. I mean, there are different kinds of possible targets. The target is the actual material in which you shoot your laser and in which you excite the plasma wave. If you use in this case, you can use a gas jet coming out from this nozzle here, which is right the size of 1 or few millimeters. The original proposal was laid down in this 1979 paper by Tajima Dozen. Then, of course, it took a few decades to arrive at getting good results. The first, I would say that the cornerstone here was this in 2004 with the simultaneous publication of 3 papers reporting the acceleration of high quality beams. And then, of course, since then, many other results have been reported, and we are now in a mature phase to use these kind of sources for applications. So coming to the core of my talk, why we are thinking and pursuing the applications of these kind of accelerators in medicine, and in particular in radiotherapy. You know that I think that you know. I mean, the cancer cases worldwide are increases. The number of new diagnoses, which could be, and hopefully it's due to a better access to diagnostics. And radiotherapy, although of course many new immunotherapy treatments are coming into play into the field. Radiotherapy is still considered, and it is considered for the next years, for the next decades, a cornerstone of many cancer treatments. Of course, it's not used in all the cancers, but for many cancer types, radiotherapy is a cornerstone of the treatment. And of course, there is an increasing demand for radiotherapy machines. And then, of course, as we will see in my talk, there is a possibility of introducing novel protocols in radiotherapy thanks to the usage of electrons. So here you can see some figures. There are roughly at the moment 20 million new cancer cases that can diagnosed each year. The more than half of the patients are treated with radiotherapy, either with curative or palliative intent. And of course, the market size is exploding. So, what is the current scenario in radiotherapy? As you know, the most common radiotherapy protocol nowadays is use the Bremsstrahlung X-ray emission, so gamma ray photons, which you produce starting from megavolt clinical radiofrequency linears, typically 1 meter in size. So due to of course to the limitation in the Linux sites, again 1 meter or so, the maximum energy of the electrons which you accelerate is limited to at the moment to roughly 20-30 MeV. Of course, these 20-30 MeV are not suitable to directly treat deep-seated tumors. Which means that you have to convert these to generate secondary radiation, so gamma ray photons, starting from these electron beams. And of course, as you know, photons, MeV photons have much larger penetration depth than electrons at this energy. There is an exception, of course, which is the intraoperative radiation therapy, but this is, I would say, rather not very common. Now, what is of course, radiotherapy has many decades of history, so it works. But of course, there are some downsides of photon radiotherapy. Of course, rather poor directionality. You are basing your generation on Bremsstrahlung. Broad spectrum, and of course, long attenuation length in human tissues, which means that in order to, if you treat a deep-seated tumor, you of course have those deposited over even beyond your target volume, which is the tumor. And this, of course, in order to increase or improve the conformation, which means targeting with more precision your dose to the tumor, you rely on, I would say, relatively advanced X-ray modalities. I can cite intensity negative radiotherapy, and of course the multi-field radiation, which means that you use several directions of irradiation. And then of course these are the two I would say bricks. And then of course over the past I would say 10 to 15 years a lot of improvements, technological improvements have arisen in this field. So, what about using electrons to directly irradiate the body, the tumor? Well, of course, early studies on this field dated back, I would say, 30 years. But at that time, of course, the studies employed relatively low energy electrons, up to 50, 60 MeV. And these electrons at these energies show a relatively shallow penetration, quite bad dose deposition profile due to scattering, which results in high transverse dose spreading. And then, of course, there is a high range struggling. And then, of course, even the propagation of these electrons in air between the exit of your accelerator and the body is an issue because of the spread, of the scattering in air. Then, of course, I would say 20 to 25 years ago, the usage of electrons with higher energy, so in particular with these in this range of the so-called very high energy electrons, VHEE, started to be studied, mostly by means of Monte Carlo simulations. So, for instance, here, this is a relatively old paper here, 20, yeah, I mean, 15 years ago. It was published 15 years ago. It was one of the first comparison between possible, of course, via uh, simulations, Monte Carlo simulations, comparison between the effectiveness in terms of we will see. I mean, in terms of quality, then I can be more precise in a moment. Of the treatment between a conventional radiotherapy device, this one, 6 MeV, based on 6 MeV X-rays, 6 megavolt yeah, X-rays, and a possible radiotherapy machine using 150 MeV electrons. And of course, the potential was shown in this paper for good dose conformation using electrons, comparable or even better depending on the organ and I mean, to the one which can be achieved in conventional radiotherapy. There is also another good news for I mean, advantage of the usage of very high energy electrons in radiotherapy with respect to conventional therapy, which was discovered actually, which was studied relatively recently, which is the relatively reduced sensitivity of the electron propagation and of course of the dose deposition profile with respect to tissue inhomogeneities. For instance, this is these two pictures here, these plots here, shows the dose pattern or the dot deposition pattern of conventional X-ray, photons, gamma ray photons, and VHEE electrons. In the case of the presence of a bubble of air here. And as you can see, the dose deposition pattern in the case of electrons is relatively unperturbed with respect to what you would expect in the absence of this bubble of air. More recently, I would say 15 years ago, roughly, the so-called treatment planning systems, which are softwares and algorithms aimed at optimizing the dose deposition using different geometries, geometries, intensities of the beam, and so on, started to be used for checking, for assessing the quality of radiotherapy treatments based on VHEE. This is one of the first paper published. It's dated of 2015. And here you can see, I mean, these are so-called dose volume histograms. Each histogram basically shows the in the y-axis here, the percentage of, I mean, at a given target dose for your tumor volume, it shows, each curve here shows the percentage of the volume of each organ. So each curve corresponds to a different organ or tissue. Which is delivered to that organs. So ideally, you would like to have here a flat curve to 100% here for your tumor, for your target volume. It's the red curve here, PTV, planned target volume, and zero dose here for all the other organs. But of course, there are some, some dose goes into the surrounding organs. But what you can, I mean, the message from this kind of plots here, if we look at this for instance, here, You can see from here that WMAT refers to a conventional radiotherapy protocol, and VHEE to a possible therapy with electrons. What you can see from here is that depending on, of course, on the kind of tumor which you are considering, you may have that the treatment with VHEE electrons can be better in terms of quality, so in terms of dose distribution between the target volume and the surrounding tissues with respect to conventional radiotherapy. So more recently, other appealing features of possible radiotherapy with electrons have been considered, even in the laser-driven accelerator community. So this, for instance, is a recent paper from, a few years ago, from the group of Strathclyde, in which they studied the possible advantages of focusing the electrons to locally increase the dose. Of course, you cannot do this, or at least you cannot do this very easily with photons. And of course, they ended up showing that in principle you may have an improved tailoring of the dose. But there is also another aspect, another issue, which is the possible better management of the motion, of the physiological motion due to the breath, possible management of the dose delivery with electrons using fast magnetic scanning, which, for instance, can be synchronized to the human breath. Then a few years later, so 3 years ago, sorry, there is no, I think, yeah, 2021. This is a paper by the group of Lund, in which they first, they showed the transport of laser-driven VHE beams to a phantom, and they also carried out some dosimetry on this phantom. More recently, I would just, of course, there are many groups, I will show later, there are many groups working on this in this field. Quite recently, this is a paper of 2025, the Chinese group led by Professor Wei Lu is very active in the field. So this is one of their last paper. They have a very compact laser system, and they are using this scheme using permanent magnet quadruples to improve the pointing stability of the electrons, and then a copper plate to homogenize the dose. So these are some of the results which they obtained. Just look at this plot here, for instance. This is the distribution of the pointing with and without the quadruples. And then this is the dose taken by a Kafka film at the point of the atomized. So they performed the preliminary experiments aimed at investigating the efficacy of these electrons in controlling the tumor in mice, and they got very nice results, as you can see from this picture here. So as I anticipated, there are many groups working on it. For instance, in Europe, in Paris at LOA or in Paris Sud, even the CERN is very active in this field, of course, pursuing a conventional acceleration. And then there are other groups at Strathclyde, Lund, as I mentioned. We are working on it, LI, and so on. And of course, the groups from Asia. As it will be clear in the following, of course, real applications possibly would require a higher average power laser sources, so higher repetition rate lasers. So very quickly, come to the just to want to show you some recent results from our group very quickly. So the one of the first experiments which we could perform was aimed at demonstrating the possibility of tailoring the loads, which such a kind of beams, tailoring the dose in a similar way to the one used in conventional radiotherapy. So just for those of you who are not aware of this, in conventional radiotherapy, you of course have to I mean, your aim is to deliver most of the dose to the tumor and possibly sparing the surrounding organs. And you do it by basically building your dose deposition profile using. I mean, you start. I mean, the beam from the X-ray beam or gamma ray beam, sorry, is relatively large, and you cut different pieces of the beam using such a so-called multi-leaf collimator, which you adjust based on where you want to put you want to deliver the dose, and then you I mean build your your target dose deposition pattern by using different um, different apertures, different configurations of these multi-leaf collimators and different fields. And we made something similar. Of course, in the case of a laser-driven accelerator, your beam is smaller relative as compared to a conventional gamma ray beam. So we made such an experiment here. Don't have time to enter into the details, but we have shown that these beams, so pencil beams, very small beams, 3, 4 millimeters beam, large beam, large beams, can be used to, for instance, deliver the dose, most of the dose, to a target, sorry, a target volume inside a phantom here, for example, using irradiation similar to the so-called multi-field irradiation used in the conventional radiotherapy. So this is the real experiment. This is the comparison with the Monte Carlo simulations. And as you can see, there's a quite nice dose deposition profile here, which, I mean, I'm just saying that the dose here is 3, 4 times the orders, so the dose which you have to deliver here and close to this point. And at the same time, we try to mimic the conformation of the dose in a similar way to the one used in so-called the IMRT. IMRT stands for intensity modulated radiation therapy, in which you modulate, so change the intensity of your beam according to a given pattern, which you of course have to identify in advance. And we did it by just, of course, delivering a different number of shots to the different points here. And in the end, we were able to show that this kind of electrons can be used for tailoring the dose with a millimeter size, with 2-3 millimeter resolution. Now we are working on, for instance, just to give you a taste of our activities, on assessing the potential of these VHEE electrons for treating deep-seated tumors, for instance, with respect to using real cases. So, for instance, here we are working on a tumor located, a brain tumor here. So we developed our own tools, Monte Carlo tools, using based, of course, on Gen 4. Taking directly the CT scan of a patient and optimizing the irradiation in order to to target a given volume. So these are some of the results we are now getting. The results are quite encouraging, as you can see from again. This is again the wedge dose volume histogram plot here. So once again, to remind you, ideally you should have this red line sort of step function here, and these lines here as low as possible. So there is we can achieve a quite nice target coverage in the majority of the volumes. Sorry, of the target volume or the tumor. And then, of course, there are some other considerations, but the message here is that using pencil beam electrons, VHEE electrons, as the ones which can be accelerated from provided by laser plasma accelerator, you are already in the position to have a similar dose deposition pattern in terms of quality with respect to conventional therapy. Now, of course, these results can be improved if you had access to the so-called flash effect. I think that most of you knows this flash effect. It was just to remind you, it was an effect which was a radiobiology effect, which was rediscovered actually in 2014, which basically consists in the fact that ionizing radiation delivered at ultra high dose rate, we'll see the number in a moment, the figures, can show a reduced toxicity in terms of different biological endpoints in healthy tissues or organs, and a comparable or even better tumor control capability. So this is the plot from the first paper reporting this effect. So just to let you understand, this is the damage induced, unwanted damage induced in mice in terms of pulmonary fibrosis after the irradiation of the thorax of these animals. So of course, this red line corresponds to a conventional irradiation, so 1.8 gray per minute in their case. This is the typical number of dose rate used in nowadays radiotherapy. And this is the blue curve here shows the results, corresponding results for ultra high dose rate. And of course, the difference is very sharp. Now, I have to say that, of course, as maybe most of you know, there is, I mean, the understanding of the underlying of the picture, the underlying processes giving this effect are not clear. Even the conditions in terms of dose rate, and so on are not clear. There are some hints, of course. So, for instance, here you see a plot showing the results of some experiments in terms of dose per pulse in gray here and average dose rate here. Now, the fielded points corresponds to experiments in which this flash effect have been observed, and the empty points here to experiments in which, on the other hand, no flash sparing was observed. So there is, looking at this picture here, for instance, you can guess that there's a threshold in terms of dose rate for this flash effect to occur. And at the same time, there's a threshold in dose per pulse. And similarly, this plot shows the dose rate in the pulse and the irradiation time. Again, fielded points correspond to experiments in which the flash effect has been observed. So in the end, these are some of the numbers, of course, with some yeah, I mean, not very strict. Some of the figures which are deemed to be required for this flash effect to be observed. So dose rate greater than 40 gray per second, total dose in the pulse um, higher than 2 or 10 grays. The radiation time has to be relatively short, and the instantaneous dose rate has to be greater than these numbers here. Of course, then even the role of the structure of the time structure of the pulse is not very clear. There are, of course, some ongoing. I mean, the first patient was treated in, of course, on a compassionate base in 2019. This was reported such a treatment of subcutaneous lymphoma, and there are, of course, some ongoing trials on humans. Uh, Even the biological mechanisms, as I was mentioning, is not very clear at the moment. There are many ongoing experiments. There are some hypotheses. I don't have time to to dwell on this. Just to mention, there is one of the first hypotheses which was made in order to explain this mechanism is the rapid depletion in the case of a very high dose rate of oxygen, which means, I mean, most of the, I have just to mention that in the case of relatively low lead radiation, such as electrons, most of the damage can be actually due to the formation of so-called ROS clouds. ROS stands for reactive oxygen species, which results results from the from chemical reactions induced in water, similar by the radiation, which then leads this ROS species lead to the damage of the DNA. So in the case of a ultra high dose rate, you have a rapid depletion of this ROS species, which means the onset of a transient protective hypoxia, which leads to the different production of this ROS and to a sparing of the damage induced by this ROS. But there are also some other hypotheses, for instance, the so-called immune hypothesis, which means that, of course, if you deliver the dose in a smaller time, the same dose in a smaller time, there is a reduced amount of circulating blood lymphocytes which are exposed to the radiation. Then there are other hypotheses. You can just mention the reduced inflammation and other mechanisms. So these are some recent papers on the radiobiological study aimed at clarifying this flash effect. This is taken by a recent review from our group. As you can see from here, the results are quite are not I mean not quite I would say contradictory. So, for instance, and they actually depends on the organs or on the organ or on the tissue which you are looking at. So, for instance, in lung, which was as we saw the first organ which was in which the flash effect was discovered. This flash effect is quite in lungs. It is quite consolidated. In brain, all the experiments have given quite consistent results. On the other hand, in skin and bones, the results are quite controversial, even suggesting that over a longer term, the ultra high dose rate can be not very good in terms of effects. Intestine, this is again a quite controversial case. And then, of course, there are some other results in other organs. So why I'm referring to this flash effect? Because, of course, in order to have a high dose rate, ultra high dose rate, possibly, to access this flash effect, of course, it's quite difficult to have this ultra high dose rate if you go through the Bremsstrahlung conversion, just because the Bremsstrahlung is a relatively inefficient process. So the I mean the using directly the electrons for accessing this regime is at the moment considered quite the main way. And if you want to treat deep-seated tumors, of course you need very high energy electrons. And in order to produce very high energy electrons, you need either relatively long conventional RF linacs, although there are many technological developments in this field, primarily from CERN. Or you can use, of course, more more compact sources, accelerators, as the laser-driven accelerators. There is one more point which has to be considered for laser-driven accelerators. This is a peculiarity of, and I think you are already aware of that. Although even though of course I mean these are the dose rates required for conventional and flash treatments. As we saw from 2-3 slides ago here, the instantaneous dose rate for taking all these numbers together, the instantaneous dose rate for the flash is for the order of 10 to the 6, 10 to the 5, 10 to the 6 gray per second. And you consider, of course, if you have to consider the pulse duration. I mean, you know that VHEE beams from laser WakeField acceleration are very short. So this translates into the fact that the instantaneous dose rate of laser-driven accelerators is actually much higher than even the instantaneous dose rates needed for flash. And this, of course, could possibly result in novel radiobiology phenomena, which can be studied by using this sort of accelerators. So this is I have this slide here which just gives you an idea of our ongoing experiments on radiobiology. Of course, each group has all the groups working in these fields have developed their own setup for irradiation of samples or animals. But I just want to mention to stress this value here. This is the dose in gray, 0.27. From the single shot. I mean, of course, this is our experiment, but this is a quite established number. I mean, at least the order of magnitude. So from when you have laser-driven accelerators, the dose per shot is of the order of a fraction of a gray, which means that if you want to to have this dose rate needed for the flash regime, you have to have higher repetition rate lasers with respect to the ones which are currently available. And this is where the laser, the R&D on laser development comes into play. So just let's have a very quick look at this picture here. This is the shows you some of the current laser systems operating worldwide. I mean, the most important ones. In this plot in which you have here the pulse energy and here the repetition rate here. And this blue line separates the existing from targeted, or at least non-existing, or at least targeted lasers. So, for instance, the lasers required for machine drivers for your Plaxia, for instance, stand here. But even if you want relatively smaller, laser delivering relatively smaller energy for medical applications, for instance, you have to be here, which means that you are at the forefront of current laser technology. And this is why a lot of efforts are ongoing to increase the repetition rate or the average power of ultra-short lasers. So in our case, we are, for instance, I can mention, we are just commissioning a new laser from Thales, working at, it's a titanium sapphire laser, of course, working at 100 Hertz. It's a 40 terawatt laser, which can, is meant to be used for this sort of applications, and particularly in medicine. We are also equipping our lab with a new underground bunker for this kind of applications. Looking at the longer term, if you want to increase more the repetition rate or the average power, I would say, of the lasers or ultra-short lasers, titanium sapphire-based technologies are not foreseen to allow this further step, and this is why other schemes have been proposed and are pursued by different groups worldwide. We are in particular working on this scheme, which was proposed a few years ago by Livermore, yeah, which is called which is a scheme with a direct pumped CPA, which should allow you to get much higher wall plug efficiency with respect to the current titanium sapphire technology, indirectly pumped. And it relies on this multi-pulse extraction scheme, in which you basically it basically employs a different active medium with respect to the conventional titanium sapphire, with a much longer upper state lifetime, which means that the energy is stored, the pump energy is stored in the form of inversion population for a much longer time. Which means that you don't have to extract all the energy in a short time, or put it in another way, in a single shot. You can just pump your system and then think to extract the energy over multiple shots. And this, of course, works if you have the repetition rate of your system comparable to the inverse of the upper state lifetime, as it is when you got into when you are pursuing this kilohertz repetition rate. And this, of course, also allows you to pump, and this is the important point, pump your system using quasi-continuous wave pumping, and possibly using, for instance, diodes. And this is indeed a direct pumping of your active medium using diodes. So there was a first demonstration. Thulium is one of the active medium used for this kind of scheme here. There was a first demonstration of this scheme, although at relatively low repetition rate, which means that they didn't rely on multi-pulse extraction from Livermore. This was published in 1.5 years ago. We are working on a similar scheme, and on thulium lutetia, We are aiming at building such a laser here with these specs. So 100, I would say 100 femtosecond duration, pulse energy in excess of 500 millijoules, and a repetition rate of 1 kilohertz. And we are working on it. We already studied. Studied the multipath extraction. We were able to recently demonstrate this multipath extraction um, um, scheme. So just to conclude and summarize, radiotherapy can, over the next few years, can see potentially a major breakthrough. Given, of course, there are over the past few years there have been incremental but steady, I would say, improvements, but it can see a major breakthrough due to the direct usage of electrons, and in particular, very high energy electrons as the ionizing radiation. And in this context, the laser-driven accelerators can offer a very promising technology for novel radiotherapy devices. Of course, in this frame, the possible exploitation of this flash effect is playing a major role and is pushing for research in this field. And of course, the radiobiology of VHEE and flash effect has still to be studied, and there is many work to do in this field. And also research and technology development, both in the electron acceleration and in new ultra-short lasers with a high average power is ongoing worldwide. So that's it. Thank you.
Thank you very much, Luca. That was great. Really interesting. So if anyone has any questions that they would like to ask, could I please ask you to put those in the Q&A now? We'll just give you a couple of minutes to do that, and then we will put those to Luca, if there are any. So just pop them in the Q&A, if you could, please. Okay, so we've got one. What are the possibilities of considering GeV level beams for radiotherapy?
Well, to be honest, at the moment, I mean, GeV means that you have a very, very long propagation, very long depth. As far as I know, I mean, this VHE beams, VHE range is the ideal one for carrying out radiotherapy, even because there are some very, very important issues, which of course have to be clarified in a better way concerning the radio, secondary, the activation of materials, even in the body, from this kind of electron radiotherapy. So this has to be, this is a very, very quite a hot point which has to be studied. So to be honest, I don't have an answer, but I would say that for at the moment, most of the groups are working with this on this VHE energy range.
Okay, thank
And
you,
of course,
Luca. Sorry.
I see it. I mean, the usage of GeV of electrons accelerated to up to the GeV range can be possibly seen as a way to generate secondary radiation using I mean, much more advanced schemes than the one, of course, used in current radiotherapy. So, for instance, Thomson scattering, and in that case, there could be a very, very, very strong interest in using this kind of electrons for radiotherapy.
Okay, great. Thank you, Luca. I've got another question here. What charge range would be ideal for VHEE beams aimed at medical applications?
This is actually a very important point because you ideally want to even if you, I mean, in order to us to access the fresh regime, of course, as I mentioned, the main route is to increase the laser repetition rate. But of course, if you had a higher charge with respect to what you have right now per shot, that of course would would relax your requirement on the laser repetition rate. I would say that at the moment, most of the experiments are performed with a charge in the VHEE range of, I would say, a fraction of, I mean, several tenths to hundreds of picocoulomb. Of course, ideally, there are of course some ongoing activities even from our group. You want ideally to arrive at nanocoulomb or more.
Okay, thank you. Have another question as well. The question is, are you building a focused VHEE beamline at IL?
Yes, we are working on it. Yes, we have some path to do, but we are working on it at least at this stage from the simulation point of view.
Okay, great. Thank you. We'll just wait a minute in case anyone has any more questions that they would like to pop on the Q&A. Okay, I think we're good. So again, thank you very much, Luca, for your time and for your presentation today.
Thanks to you, Anna, and
Um,
to everyone.
it's been great. I'd also just like to remind everyone of the next seminar that we've got. So that will be on Friday, the 6th of February. It will be at the same time, so 11 a.m. UK time. And we will be joined by Dan Symes, who is an experimental operations manager for the Gemini Laser Facility in the UK. And his talk will be on plans for Laser WakeField Acceleration at the UK Extreme Photonics Applications Centre. So please join us for that as well if it's of interest to you. So wishing everyone a nice day, and thanks again to Luca. Bye, everyone.